Fine, sir.
So, okay. So first of all, I'm very thankful to Dr. Ravi for a nice introduction and elaborate introduction of mine. Yes, some things I did it with the efforts of my students and with the efforts of my colleagues, and all together we have achieved this much. And I'm also very thankful to Dr. Nanda and for inviting me, and Dr. Ravi for inviting me on this prestigious FTT faculty development program, which is especially like 5G and beyond wireless communication that I know. So I thought like initially I was, as I Ravi said, that I'm just trying to elaborate that how the Leo is going to be uh, implemented, and it is useful for the 6G communications and to provide the global connectivity over here. But due to my some health restriction, I'm going to restrict myself with 5G and beyond wireless communication challenges. And just I will talk about the paradigm shift that what we have seen in this area. And probably like some two or three open research problems, which I will open and leave it for the audience that they can work on it, or they can just find out some ideas that how we can solve it on these problems, or how we can work out to achieve the 6G and all these things. Okay, so thank you so much, and let me share my presentation. And with your permission, I'm just going to stop my this
Video, sir. The video.
what is the complete screen, I think, na? I have to go for a screen, the complete screen, na?
Yes, sir. Full screen of the presentation.
One moment. Okay, this is what it is asking me. Okay, my screen is visible.
Yes, sir. Your screen is visible.
And is it in the full screen mode? Is it?
Yes, sir.
Okay, hopefully it is visible.
Yes, sir. It's visible.
So, like as I said you that today's topic that what I'm giving, and since last week onwards, you are listening about that what are the things happening in the 5G and beyond wireless communication, and what we are going to make the proposition, or matlab, the things technologies we are going to use in the next wireless communication paradigms. So I will just say that it is a paradigm shift in connectivity, that when we are moving from 5G to beyond 5G. So in the 5G, we usually talk about like faster speed, lower latency, and the massive device communications, and with the help with this three parameters, or three things that which we are able to uh, enhance the AR and VR and smart city connections and all these things in this. So if I start with my one moment, why it is not changing? Yeah. So if I see that why this we are talking is still like 5G is there, and we are talking about that we are getting a good speed. We are able to connect the smart cities. We are able to get the AR VR enhanced connectivities. We are using in the lot of applications, the IoTs, the massive IoTs that which we are able to connect it to the devices that which we are connected. But it's still I will say only like the 40% of the world is still lack of reliable broadband connectivity. That is the thing which force us to think that what is next. The urban networks are advancing, and that's basically this is giving you the slicing between the geographical ways, that the urban people are getting the networks which are really advanced, and they are getting the good connectivity, but the rural and the remote areas remain unreliable. So they are not getting, we are saying that we are reaching to them, but the connectivity as well as the speed that what we are receiving over there is totally unreliable. So to achieve this, what we can do? We can do one thing, that is the satellite terrestrial integration may offer a realistic global scale solution. So that is the major talk initially I was want to give it, but now I will just say one line, that is a satellite terrestrial integration, that is STI, may provide you the realistic global scale and solutions. It will brings a lot of problems that we will see it over here, but actually if you see, because that will make uh, our infrastructure is free of the base stations somehow, or maybe some less number of the base stations, and the connectivity even in the disasters, even in the rural areas, even in the remote access, we are in a position to get the connectivity. Only the thing is that people may say that okay, we have a geo, but naturally when we talk about the geos, they have a lot of latency is there, so we have to bring out it to the lower orbits. Like we can talk about the MEO, we can talk about the LEO. So we will realistic, because in the 5G there is a the one layer we are talking about, also the LEO integration, the satellites over there. So that's why this is a feasible uh, possible solution that which we can give it to make the our whole world to be connected. So just to give a glimpse, like as we know, the 1G is basically voice, 2G is for digital voice and SMS, 3G for internet access, 4G for mobile broadband, 5G what we are talking about right now, it's the lower latency, high capacity and IoT scale networks. And what we are talking beyond 5G and 6G, basically we all talk about the ubiquitous intelligent connectivity. The intelligent means like we want to incorporate the some intelligence into this, and merging satellite and the terrestrial is the possible solution for achieving the beyond 5G and 6G, beyond 5G and 6G over there. So this table will give you the progress in which the how we are progressing from 1G to 6G. We have progressed a lot from in terms of the speed, and we are demanding much in 6G. And the services what we are providing from 1G to 6G is also changing, and it's also evolving as we are evolving our technologies also. Like from 4G onwards, we talk about the HD video and VoLTE IoT service things, and when we talk about the 5G, we are talking about the multiple connections we are talking about the IoT, we are talking about the AR and VR into this. And when we talk about the 6G, the new definition has to be like intelligent network, that is the AI native networks comes into the picture. And we talk about the hologram and the digital twin concepts that are coming to the pictures. Then, and for that, we are trying to develop the beyond 5G or the 6G networks. Or we don't know like whether we call the 6G or simply we call the beyond 5G, because in India if you see like 4G is the advanced 4G is like 5G we call it. So the same way, like because we have not installed or deployed the complete 5G networks, we have just do the enhancement in the 5G. Some places we are doing the complete change in the 5G network, but most of the places we are working with the for enhanced 4G networks, and we call it as a in terms of the higher speed which we are able to achieve in the 4G is called as 5G networks. The session that what we are going to figure out the basics of 5G, beyond 5G vision, key challenge, satellite integration, then key challenges and the application, the case studies that probably which I can see some of the. So if we see the first, when we talk about the basics of the 5G, the first point comes as a spectrum. So we have seen like two types of the spectrums, like in which like 3.4 to 6.0, which is the 5G near new radio, and the another one is the millimeter wave where we work for 2.24 gigahertz to the other range, and to the 100 gigahertz of this. And that is the basically the coverage as we are looking towards this spectrum. Then how we going to cover, like if you see the 5G new radio millimeter wave, which gives the 5G gigabit 5G communication, this is n times of 10, and finally we have seen the broader coverage will give the ubiquitous this LTE. Then In this 5G spectrum, we are thinking of the millimeter wave mainly. That is initially that is 24 to 100 gigahertz, which can support our very high data rates, wide bandwidth, higher capacity wireless communication, and naturally, but as we get the benefits, we have to get the cons also. That is the high path loss, limited coverage, and all these comes with the picture. This picture will show me that what are the things that which we are which we see is like very wide bandwidth that which we can achieve with the millimeter waves where it is. Second one is the shorter wavelength that which we are in which we can make the very small antennas or the massive MIMO antennas can come into the picture, that we'll see it later on. High path losses that we have to suffer for that, and poor penetration level because of the higher bandwidth, and the ideal for short range and high capacity scenarios. This is what the points that which we can pick it from this 5 millimeter wave concepts over there. The the this the spectrum that what we are talking and what we are using in this is basically the three types of spectrums that we generally use, like specifically exclusive use license spectrum that which we are giving. The some are the shared spectrums where the different countries are going to use it, and some are unlicensed ones which anybody can use it over. So in that, on three types of the spectrums that which we have using the 5G, divide the 5G spectrum into this way. So as I told you that we are working for this satellite network accessing, which the 5G has incorporated. That is the Ka band, which is operates from 24 to 40 gigahertz range, and offering the high bandwidth and the higher data transmission rates over there. And the lower than this band is 12 to 18 watts, which is basically for the satellite TV broadcasting and for the broader coverage. That bands that which we can and in which we are talking about the mainly from 26 to 40 gigahertz of the band for the satellite network accessing. The if I say the this is the spectrum that what we are talking. And if we talk about the 5G architecture overview, so for 5G consists of the radio access network and a transport layer and a core network that uses a service-based cloud-native design, and separate control and user planes are there. So that is the architecture in which like we are a radio access network, a transport layer, and a core network which can provide the service-based services, cloud-native designs, and the separated in which the separated control and user planes are there, so that we can give a more accessibility. So ran with massive MIMO with beamforming, sorry, and one moment, why it is, yeah, and the service-based architecture in the core, and the cloud native network functions, and the MEC for the latency critical applications. And these are the main four core points that I've considered over here. So if we see into the radio access network with massive MIMO, so if you see, this is the 4G and 5G networks. As I told you, in India, we are using the advanced enhanced 4G networks. So if there is a backhaul which is going to be connected with the critical centralized units, and the mid haul which is going to be connected with the distributed network, and the front haul where it is connected to the radio unit, basically the user units over there. And in that, we will handle basically the signal transmission, mobility part, resource scheduling and interference, and as well as the quality of service delivery part, that which we are handling over there. If we see, because as I told you, the massive memos that which we are using. So massive memo, as we all know about that, what do you mean by the massive memo? It in a wireless category is a very large number of antennas. Maybe as we talk about this 5G, in which like millimeter waves that which we are using, so hundred and thousands at the base MIMO antennas can be connected at the base station and serve to the multiple users simultaneously. So as you can see in this figures, like here every user has their own means uplink to these base stations, and from with the help of the beam forming that which we are giving it to the individual users, and we can serve to the individual users over there. So if you see over here, so beam forming is nothing, this picturization will show you when send the electromagnetic signal to a particular direction rather than sending on all directions. So if you see, because previously what we do, we used to transmit in all directions, and here with the beam forming, we are particularly towards the sending the data towards the user, which we want to be communicated. So in that, the adjustment towards the phase and amplitude of the transmitted signal is going to be required, and beamforming is formed by the reinforcing the signal in a particular direction. So there is a mechanism that by which we from which we are able to search the users where we have to transmit the data, and on that basis we can make the phase where in which we have to transmit this data over there. So this is the basically the massive MIMO concepts, like where we can find out the efficiency, the beam forming that which we can give the connectivity and mobility, flexibility and security, higher data rate, capacity and the speed, along with the quality and reliable throughputs, power saving, coverage, and the processing that which we can achieve over there. The second point that which I talked about is the service based architectures. So in which the service based architectures, there are the four functions that which we work on. Like first one is the network exposure function. Another is the network function repository, policy control functions, the I would say the user defined managements, and based on that there is a separate control plane and the separate user plane to take the decisions. And the control plane, basically it is going to authenticate accessing, and session managements will be taken care by this control plane. And then in under the user plane, we will give the access to the radio access network user plane function as the, and along with the user equipment individually for the data networks. The uh, the third one, as a core architecture, the third one is the cloud native function, in which the cloud native function, it's nothing but a modern approach we used to say to for networking, which leverage the cloud to simplify the scale networking function, and which gives the advantage in terms of the scalability, in terms of the efficiency, in terms of the multi latency, that what we can get it, we can get the velocity, quick rollout, that we can deploy our networks in a very easy and the faster way, and the ubiquity, like in terms of like we can manage the networks from anywhere at any time. So that's the advantage what we get it in the cloud native networks. And there are a lot of applications where we are using this cloud native infrastructures, and for that uh, we don't have to put a dedicated hardwares over there, because that everything is in the cloud, and we can achieve the benefits that what we getting with the clouds over there. This this is basically the I would say the edge computing part, in which this is the fourth core, in which the MECs in the mobile network is distributed. This is the mobile edge computing part we are using. It is nothing but the distributed computing paradigm with the computation and as well as the cloud servers that which can do that. With this, we are able to achieve the latency, the low latencies, that part, and the most of the things we can work out at the cloud servers itself. Oh, sorry, edge servers. So that will help you to process the data with in a bit faster way of that. So this is the mobile edge computing, and in which the benefits of this, like as I told you, the low latency, reduce black hole loads, better security, privacy, high reliability, and real-time implementation of the AI that we can achieve. Sorry. Um, the low latency, basically, it depends on the applications. So generally, the applications where the autonomous driving and industrial robots, where we need the low latency, can be used this 5G communication connecting between the 2 points. The high reliability, basically the edge nodes can continue functioning even the cloud connection is unstable. So because for cloud connection we need the connectivity from device to this, but edge nodes, they itself have the computing power and all the things. So that's where it increases the reliability of the whole system over there. The concept, another concept is called the network slicing, which comes over here. So network slicing, basically it will gives the benefit that in which the operator creates the multiple and independent virtual networks on a single physical layers. Okay, so as you can see, the each slice, means once we divide the physical layers into this different parts, so each slice can be customized with a specific performance and characteristics which have the security levels, quality of service requirement to cater the different applications. The advantage, like for the different applications, we can use the different requirements as the vendor is demanding or as the user is demanding. So in which like higher bandwidth video streaming, low latency communication, and mission critical business apps can be work out. So if you see the enhanced mobile broadband, that is EMBB, ultra reliable low latency communications, which is the URLLC, massive machine type of communication. This is MMTC. So in this, if you see this, I have shown the what type of applications that which we can generate it with that. Or for the ultra reliable latency, in which we have seen the medical as well as the autonomous driving is required. And for massive multi-machine type communication, in which the massive IoT systems and the automation in the industries can come into the play. So if we see what is ultra reliable latency, basically a subset of this is nothing but the subset of 5G, as it is a property, or it will give you the ultra reliable low latency part, which gives you the uh, ensure that more efficient scheduling of data transfer, achieving shorter transmission through a larger sub carrier, and even scheduling overlapping transmission. And with these applications, what we can achieve, these are the applications that which we can achieve. This is, I have given the reliability or latency application definitions, which we already know about that, what is reliability and what is latency over here. So this next one is like massive machine type communication, in which uh, we will make the communication to be effective, in which IoT devices can communicate easily, or the not only the IoT, the autonomous vehicles, that they can work easily, communicate easily. The devices ultimately is going to connect it with the MMT. So in this, like as in this figure, the device to device MTDC, the MTC, mobile connected, device connected. So all type of massive machine are going to be connected, and lot of applications that which you can cover into this. So this is the like the previous one, and this will tell you that how this massive machine or the ultra low latency that create and these applications where we can use this. So if we see the 5G in real deployment, like this is the standalone deployment, this is the standalone deployments, and this is the private 5G network deployment. So as I told you, basically the India, Europe, Gulf, and Southeast Asia, we have used the 4G LTE core with 5G new radios, which will help to not fully deploy the 5G, but 5G capabilities are embedded into that, which is the help in quick rollout and low cost. But uh, the latency that which we are achieving, or the true network slicings which we are not able to achieve in this network standalone. This The standalone is basically the native 5G core, which basically enable the URL, network slicing, private 5G, MEC, and true industrial automation. So in which the 5G technologies on the base of that which the 5G was designed, that all are going to be deployed. So basically, this China Mobile, Unicom, Telecom, T-Mobile USA, Vodafone, Dutch, they have implemented the 5G standalone. So that way, the full 5G functionality we can achieve, but still the problem what is that naturally the high investment and the complex integration is the problem. But some countries have done it, and that's why the countries which are in the developing stage, they have used this. And the private 5G network, excuse me, the the private 5G, basically it is an enterprise deployment. So this is the license band that N78 in Europe, and shared spectrum. Like as I told you that we are using the different three: dedicated, shared, and the unlicensed one. So in that, high reliability, because as we are using the spectrums, specifically dedicated bands that which we are using, to high reliability and low latency, security, and the customizable performance that which we can achieve with that. But the problem again with the complex integration with the IT and the other systems, and limited ecosystem maturity, because it is a specifically for the private enterprises that which we are employing. The If we see the advantage and the strength and the weaknesses of this all we know. The 5G technology which we are which the India has deployed, or we are going to deploy or extended in other developing countries. So advantage for this, we are all looking towards the 5G, but naturally to deploy in a means standalone SA. So it is becoming extensive, non-compatible with the old devices, require more towers, and the security issues may come. So in this, why, if we see that this is 5G strength and weakness, and till now I have talked about the 5G. If I say the why 5G is not enough, so the 5G is like, first we have applied this millimeter wave does not reach to the far, because it is of the short range communication we talk about like this. The emergencies often damage terrestrial infrastructures, like disasters. Whenever it comes, it will break the terrestrial connections and the infrastructure. That's a problem. The rural areas, we are still not able to get the connectivity, because the operators feel that it is unprofitable, or they don't want to invest that huge amount of the money over there. And fourth thing is that the maritime aviations, deserts, mountains, huge connectivity gaps. So like we cannot get all connectivity throughout with maritime aviations and the deserts, and for that we all have to depend on the satellite communications over there. So like this because of this, even though we have incorporated a lot of technologies into the 5G, inbuilt into the 5G, but still we are not, this 5G alone is not enough. So for that we need to fix up this gap, and the fix up satellite close these gap effectively. That is the thing, and that's towards we are forcing us to move toward the beyond 5G, or towards the 6G networks. So beyond 5G, basically 5G has not met its full theoretical targets, and that is what we talk about the 5G beyond. So the as we have promised, or when we define this 5G, we used to say the 1 millisecond latency. We have said ultra reliable communications. We have said massive IoT at scales that which we can make it connectivity, the millimeter wave everywhere that which can. So these things the theoretically what we have proposed in the 5G, but still we are not in a position to achieve that. So that's why the 5G, beyond 5G is needed. and in which the real deployment reveals the practical limitations of the 5G. And that's why we move towards the beyond 5G. And future application and the global connectivity demands requires more intelligent reliability and coverage and energy efficiency than 5G can deliver. So naturally, we are looking towards the 5G, and these are the challenges in the 5G that we have faced. And to improve, to mitigate these challenges, we are moving towards the beyond 5G and the towards the 6G communications. And this is, I would say, the it's a world moving toward internet for everything. This is also one of the reason where the global IoT expected to exceed 10 billions of the devices is going to be connected, and the lot of specific applications are coming into the picture. The terrestrial satellite integrations becomes the main one of the main solution for the 6G or beyond 5G networks. So if we see that how we are going to define the 6G, we generally define every technology for in terms of the target, in terms of the parameters, or in terms of the achievements that statistical achievements that which we are achieving. So like for the 5G target, we have seen the peak rate will be the 20 Gbps, and now we are thinking of 1 terabyte bits per second. So as we are increasing the peak rates, so naturally we need the more bandwidth. So more bandwidth, it means we have to move towards the higher bandwidth where we can have a more bandwidth towards the user rate 100 Mbps. So here we are saying that it should go to 1 Gbps. Latency, where we talk about the 10 milliseconds, now we are talking about zero point 0.1 to 1 milliseconds. Reliability, whatever we are reaching, is not complete. So we can increase the reliability in terms of this percentage, as you can see over here. The mobility, 500 kilometer per hour to 1000 kilometers per hour, that which we are looking. Connection density, 1 million devices per kilometers. Now we are talking about the 10 million devices per kilometers. Baseline, 10 times that which we have to make our energy efficient. Positioning, 1 millimeter accuracy, that which we have targeted for 1 millimeter, and here we are looking for the 1 to 10 centimeters. So if you see that this is the, on that basis we are defining the 6G. And as we are defining this 6G, so naturally the bands and the technologies or the techniques which we are going to implement in the 6G, that is going to be changed. And that's becomes the challenges and the future research challenges for us. So if we the first we will see the first we will see the terahertz, like the communications that which we are implemented in the 6G or beyond 6G. We are looking towards the terahertz communications, and which is terahertz is nothing but the frequency range of the electromagnetic wave, which is in between zero point 0.1 to 10 terahertz, and typically 1 to 3 are the practical systems that are working. So this spectrum basically lies between millimeter wave and infrared light. It offers user bandwidth and enabling the ultra high speed wireless links. So this features, because as I told you, if we need a if we needed this 1 Gbps, 1 terabyte so of this the peak data rate, so we need to move towards the higher bandwidth. So the first benefit that what we are getting, or the features of the terahertz communication, that it is ultra high data rate. It may be supported from Gbps to several terabytes per second. And because of the massive bandwidth, continuous bandwidth that which we are able to achieve. Extremely wide bandwidth, as I told you, then the gigahertz per channel we can get it. Pencil sharp vehicles, because at the higher bandwidth, so the wavelength is very sharp, so we can achieve the very spatial pencil beams can be made up, and highly directional communication support, spatial reuse, and secure links can be developed. And yes, short range operations need to be do, because due to the high path losses and molecular absorptions, tera is mostly suited for short range or online site communication. So this is with the advantage, some drawbacks is also there, and that we have to see that how we can sort it out over there. Um, yeah. So the first one, that the concept that we can use it here is the cell-free millimeter MIMO wave concepts over there, in which we are using the distributed access points over there. Basically, this AP1, AP2, and APN, these are the distributed access points are there, which basically serving all the users. It's not only one user; they are all serving to all the users, defining the traditional that as in the till now we are using with the cell divisions, but now the concept of the cell freeze comes. So all access points are connected to the central processing unit, and that is going to be synchronized transmission and receivers from the users, and that's why they every access point has the information about the every user over there. So the key idea, if as I told you, instead of one user being attached to a single base station, every user is served by many APIs simultaneously, improving the reliability as well as the uniform coverage. Even though if one AP is not working, so the other APs are also working. So that's why the reliability may increase, and as well as the uniform coverage area is there. So why cell free? There is no cell boundaries as you or so in that, like handover, the problem of handover, that what we are doing is not come into the play over there, and network appears one large cell-less system with a distributed antenna. So it's a completely the whole coverage of that user is going to be extended. So when we talk about this cell-free, these are the some advantages that we can achieve. So uniform user experience, high spectral efficiency, high reliability, and excellent coverage. But as the advantages are coming along with that, there are some challenges which need to be sorted out. So like these are the challenges. First, the connecting many APs to a CPU requires a large bandwidth and low latency is there. So naturally, we have to work out on this front haul load. Synchronization complexity, because all APs must be phase synchronized for the coherent transmission. So the synchronization complexity that have to work out. The scalability issue comes into the picture, and naturally the computational part is comes into the picture. Hybrid hardware variability. Different APs have different power amplifier and RF chain, so calibration is need to be is needed. So these are the challenges. Even though we are talking about the cell-free MIMO, so some advantage, with some advantage we are getting the some challenges also, and that's becomes the problems for solving it out. Uh, the This is, I think, that everybody knows, which is also going to be one of the technology used in the mature technology used in the 6G, that is the RSI, and in the 5G also this was introduced, but not in a matured way. So here what we are doing, this RSI is the reconfigurable intelligent surface. Basically, it is an intelligent reflecting surface, and wherever we have the line of sight with the receiver, we will uh, we will tilt, and which is controlled by the microcontroller, and on that basis, the higher signal to noise ratios can be achieved, and in which the basically it is enabling the network to shape the wireless propagations. So that is what we are. So this is the pictorial view of that. The next thing that what we are incorporating in the in these 6G, there is the AI native networks. So AI native networks, nothing but it is going to implement the artificial intelligence and machine learning models across every component of that, like radio access networks, core networks, transport layers, service layers, to enables to make the real time decision making, be knowledge about the conversations, self optimizations can be done, intent based orchestrating can be done, The dynamic reconfiguration based on the user traffic and environment can be taken, and autonomous end-to-end operations can be done. So like the as in the definition, the intelligent network that you have to build. So with the help of the use of artificial intelligence, we can incorporate the models which are which in all layers, and as well as so that we can achieve the this benefits with the help of this AI network. See, the another concept which I told you, that is the holographic beamforming. So it is if I say the phase, amplitude, and polarization is need to be manipulated. So holographic beamforming is based on the idea that antenna surface can store and reconstruct the hologram of a desired radio wavefront by carefully manipulating the phase, amplitude, and this. So it means the stored antenna waveforms can be reconstructed based on the phase, amplitude, and this. And that way, the HBF is often implemented in the holographic massive MIMO or the reconfigurable holographic surfaces. So if I show you this, this this part. So like if you see that these are the at one place, so that if we capture and we can make it into the different holographic views. So in optics, the hologram encode the interference pattern of light so that the original wavefronts can be reproduced and illuminated. So the antenna surface generate the holographic interference pattern, recreates a desired electromagnetic wavefront, and produce the highly accurate steerable beams in the minimal hardware complexity. So the point is that in this, the manipulation of this phase, amplitude, and polarization of the stored and hologram can be reconstructed whenever it is required. So that is the thing. So the key features of this 6G, if I say, ultra dense sub wavelength antennas elements, low cost, low power operations is required, software defined beam controls, ultra dense sub wavelength antennas need to be required. So one more thing, that is we call it as the semantic communication. Semantic communication is basically the use of AI context and shared knowledge to extract, encode, and deliver only the information that is essential for the receiver to correctly interpret, understand, and act upon the sender's intent. It means the we are putting the means we are making the communication to be AI based. So in which the only the information which is going to be shared or encoded, which is useful for the user, which is sender or the user which is going to be sent or receive. So key elements of this is like meaning over the AI bit semantic encoder and decoder, use of context, intent, knowledge bases, and task oriented things that which we can do it with this semantic communication. So if you see this this labels, so first one is the physical level, then the semantic level, and the effectiveness of the level. So transmit technical is basically it's nothing but like transmitter, physical channel, noise and interference in the receiver, and in which we can get a semantic feedback. But semantic is like feature based, what is need to be there. So semantic channel in which the semantic noise is there, features, and the semantic receivers is going to be shared. So in which, if you see, this is the knowledge source knowledge based is going to be shared with the semantic transmitter, as well as the destination knowledge base is also transmitted. And based on this, so based on the source and the receiver perception, if with the environment is going to be shared this information. So that way we can make it more effective communications. So the point which I have raised, that is the why the satellite is need to be integrated in this whole 6G beyond 5G and the 6G. So basically, we need a global coverage, ubiquitous service connect continuity, enhanced capacity offloading, support of massive IoT layers, low latency with LEO constellation, which can achieve resilience and disaster recovery, so that like whatever it happened, but this terrorist satellite integration communication will be on. Backhaul for rural and frontier networks, and foundation of the 6G services that we can get in which. So this satellite, if you see, this is the satellite orbits that just to showcase you. And we know that the LEO, the Earth orbit that which where that is amplitude is like 500 to 2,000 kilometers. So, and the next one is the medium Earth orbit, which is 2,000 to 20,000. The geo, where we usually do the satellite communications and the TV transmission and others, we are doing it over TV broadcasting and all, which is at around 36,000, and highly elliptical models. So if you see the role of LEO satellites, where it comes. So if you see, the LEO systems reduce the latency from 600 millisecond to 30 millisecond, because when we are moving from geo to LEO, only thing is that the large constellations that which we have to use, which create the global coverage, because till now the large constellation for the LEO is not, and that we have to think about. And the compatible with 5G waveform and the non-terrestrial network standards, that also we have to look into that. So that is, if we go with a LEO satellite, there is a feasibility that we can achieve the global coverage and global coverage, ubiquitous connectivity, enhance capacities. We can support the massive IoTs and all things that which we can achieve it over there. So the mega constellation, just to introduce it over, a mega constellation is nothing but it's include the thousands of satellite operating in multiple planes, covering the entire globes, including ocean and the remote areas, providing the continuous real-time coverage over there. So that's the LEO mega constellations that which we are talking, and in which the critical part for the future is satellite terrestrial integrated network, that is STIN, or are the central to 5G and 6G evolution. That STIN will be the central part for this 5G, beyond 5G or 6G evolution networks, and in which, yes, we can easily achieve the global connectivity, reliability, high throughput, low latency in terms of the broadband connectivity can be achieved over there. And in which, like, some of the countries are already working in this direction, in which the Starlink, OneWave, Amazon, Cooper are already working. So dimension is interoperability, indigenous IP, potential beam management, and the terminal cost that which we are talking. The Starlink is like this. And where the India is there, what we can do, we should push for a standard interoperable satellite system in India, which can help us. We can go for a IP creation in NTN there. We should propose its own LEO constellation with advanced beam forming and beam managements that we can do. Or India should promote standard-based interoperable terminals for low cost and a low entry barrier. So these are the things that which we can we can do it. But otherwise, these are the programs which are doing all these things over here. So deployment and the spectrum is basically rapid rollouts can be done with the help of this satellite key bands that which we can use it over here, and expanding the fabrication, small sense densification or cloud native cores can be achieved with that. So sorry, this slide should come before 5G in India, basically. What is the standard right now? Deployment is spectrum, rapid rollout in by NSA. That is the first one which I told you, and gradual migration to standalone, that which we are working. Key band 700 or 3.36, emerging millimeter, and this we are working. And expanding fabrications, small cell densification and cloud native cores for that we are working. And these are the key use cases where we can use this 5G status, or are we are using in the India. This is the pros and cons for deploying the standalone 5G. Naturally, the high capex and ruler black hole and power constraints, limited milliwave the device ecosystem. And the cons pros are like government initiative is required, is already working this, and most of the institute are having the 5G lab communication. So we all are working towards developing some more applications. Growing device affordability is increasing because as the as the research and the production is increasing, so naturally the cost of the is under affordable range comes into the picture there. So this is basically the non-terrestrial networks standards. It was proposed in the 3GPP release 17, and in which basically they talk about that how the non-terrestrial networks can work for this global connectivity. So in that it was introduced with 5G standardization. Uh, Key features may waveforms, like how we are able to communicate with this Doppler compensations, how we are able to do, and so a lot of things are there. The global 5G IoT network coverage is also there. Device to device, satellite, ruler to remote broadband backhaul, that which when resilient networks can bear. Industry impact will be there. So this is the key features that we that was proposed in release 17 for the non-NTN standards. So direct to phone satellite communication, basically is the direct phone satellite communication. And standard smartphones is there without special antennas or satellite hardware to connect directly. It gives you the coverage everywhere. Work in rural, mountain, and this extra zero extra hardware. Users normal phones can be used in this. Safety resilience critical for remote worker, traveler, and emergency responses. So, like when we talk about the direct to phone satellite communications, these are the advantage that which we can get it, and it will help you to reduce the dependency on the terrestrial towers, and letting the satellite play a tower in the sky. That is what we can say it over here. The direct to phone satellite company, sorry, direct to phone satellites, how it works. Basically, the smartphone is goes to send their information band 53 and 256 and 256 to the satellite, and from the gateways, basically the this LEO satellite for the large phase arrays, and then it will come down to the downlink. So this is the simple flow that how the direct to phone, and this is basically it's a sense that how it will work. And but this is feasible, or the 5G 3G 3GPP, they have already incorporated this NTN while making the 5G standardization, but it is not, these things are not implemented properly. So this is the pros and cons of this. So, like now we will see that the challenges when we are moving from 5G to beyond 5G, beyond this. So there are the challenges that which we have to face. So if you see that what challenges that which we can face, and that challenges becomes the problem for each of us. So as we know, the spectrum scarcity and high frequency limitations. So naturally, the spectrum which is available right now is completely utilized or overutilized. So naturally, the scarcity of the spectrum is there, and because of the atmospheric absorptions and a lot of interference, we know that frequency limitation is there. So we have to see that where we can work, and that's why we are moving from terahertz there. And terahertz bands, but still they are also suffering from the atmospheric absorption. So we have to find out that which proper band can be used. The just a moment. Nandu, 10 मिनट बाद. So the massive infrastructure cost for this, the interference management that we have to deal with it, the energy consumption and sustainability is comes into the picture. Mobility management in the dense networks. This is the first way of challenges that which we have achieved. The second thing is backhaul botal network. Like satellite backhaul still limited by latency and bandwidth. Need microwave free space optics, terahertz, backhaul maturity, mobility driven backhauls challenges, trains or airways, mein how we are able to achieve. So that we have to see. This is the bottleneck for us. The security and the privacy risk as we increases the network, expand the network. So naturally, the more attacks can be whether may be possible. So the security and the privacy risk are at cost, and that the people have to work on the device complexity. Naturally, when we talk about the multi-band, multi-antenna, so the cost of the smartphones and the batteries is going to be used. So device complexity need to be high, and we have to sort it out that how we have to make it possible. And the non-terrestrial network challenges are come into the pictures, because as we know, the Doppler shift is plus minus 40 kilohertz in the LEO. When we talk about, and LEO is whenever it is with the higher speed, because when we have the mega constellations, so every time they have to shift the because the satellites are changing and they have to do the handoffs to the different satellite which are in the view of the earth. So lot of issues, challenges will come into the picture, that we have to sort it out. The regularity and standardization delays in there, like cross country spectrum harmonization issues maybe come into the picture. So standardizations need to be done. The regulatory bodies has come into the picture to work for this, uh, to make it this possible. The uh, another thing, like when we are moving intelligent, we have to incorporate integrate the AI ML. So real time AI decisions making sorry, making the AI decision latency, because they have to take the decision. So latency is going to be in incurred into this. So AI driven RAN controls can be unpredictable without guardrails. So that we have to see. Use cases has to be readiness, like for everything like AR, VR, XR requires five milli less than 5 millisecond millisecond latencies. For health and this we are talking about 2 milliseconds and all. So we have to be ready with the user cases, because right now we are working in the 5G, we are working for the use cases. So when we are deploying it for the 6G or beyond 5G, we should be know that where we are going to use it in a proper coexistence. And as the already we have 2G, 3G, 4G, 5G, so we cannot shut down everything. We have to work out with the co-agency with the legacy networks that is already present with us. The operation and automation complexity come into the pictures, because the different types of handoffs in the from one network, from one 2G to 3G, 3G to 4G, like that type of uh, operational complexities are come into the pictures. The environmental and social economic constraints. Yes, when we talk about any things, rural inclusions, profitability, infrastructure, acceptance, lot of things come into the picture. So we have to talk about uh, the environmental and socio-economic constraints that we have to face the challenges. So these are the sorry, these are the challenges that we have to face. And if we need to move from 5G or to beyond 5G and toward the 6G, so the technologies that which we have talked or we have just seen, we have to work out on this, and with these challenges we have to sort it out. So uh, the applications, yeah, enormous. As I told you, it's not that uh, for everything there is a lot of applications that get it. So, immersive XR, smart agriculture, environment monitoring, defense, tactical communication, next generation NTN services, advanced IoT and cyber physical systems. So, smart energy grid automations, digital twins, real-time simulations, cloud edge computing applications, remote health telesurgery. So, a lot of applications are already there, which demands the beyond 5G communication or as well as the advanced communication, which is 6G there. The future scopes, there are a lot of future scopes. The expansion of the satellite terrestrial terahertz for this AI networks, holographic reconfiguration, cell-free massive, semantic goal orientations, large-scale digital twin cyber, ultra low power massive IoT systems, energy devices, energy efficient device, green network, global 6G coverage. So there are the lot of future scopes which can be come as a problem statements, and these are the challenges also which we have to handle and sort it out. So the summary, if I say that from 5G to 6G, we have to face a cluster of challenges that stretch from physics to policy. Spectrum at sub-gigahertz is crowded, and to the future terahertz bands that quickly dense small cell to the free cell uh, networks, the zones. The advanced AI-driven control brings into its own hurdles, real-time interference, model reliability, explainability. Device hardware comes into the parts which need to be support more bands, more antennas, strict power budgets. All global regulations and standardizations comes move slowly, so than the technology itself. So naturally the technology goes fast, but the regulation and all goes very slow. So together these factors define the practical barriers on the pathway from 5G to truly seamless 6G connectivity. So yes, the we want to move from beyond 5G to 6G also, but there are a lot of restrictions, and there are a lot of hurdles we have to cross over all these things to achieve this 6G, seamless 6G. So these are some open research problems, as I told you, terahertz propagation and hardware limitations that the we have to see ultra dense interference management, how we are able to do cell-free, massive MIMO scaling, energy efficient network. So these are the very few which I have mentioned it over here. And the people who are working in this 6G domain, so or the beyond 5G communication, they can work on this. Still a lot of open challenges are there which are not solved till now. So yes, these are the very good areas where we can work. The another ones like NTN, that is the Leo के साथ what we can do, AI native RAN core network challenges, semantic goal oriented communication, security and privacy gap for the future networks that we have to do it. And the finally the applications we have not yet invented will demand more of the network than anything else. So we don't know the because the initially the demand that which we are saying, that is based on our the applications which we can view, but in the futures what new applications come into the picture we don't know. So we have to be ready for the things which we still don't know. So thank you so much. This is the part, and I hope I've covered the things on time.
Yes, sir. That was good.
It was a one moment. How do I come out from this?
You want to stop the screen share?
Yes. Okay, stop is there. Yes. So like this is the general overview of 5G and beyond wireless communication and where the people can work and what are the possible, what are the challenges that they have to face it while thinking of 6G or beyond 5G. Yeah.
Sir. So quickly, if any participant has any question, they can post in the chat box. There's one, Mr. Parish Solanki.
Yeah, please.
Yeah, he's telling 5G is not enough. That's right. But many experts also warn that it will likely amplify the negative aspects of our